Hello everyone. In this tutorial series, we explain what is dead reckoning. We focus on the application of dead reckoning in mobile robotics. We concisely explain the main idea of dead reckoning, and we explain how to use a simple approach for solving the dead reckoning problem and for implementing the solution. In the second tutorial part, whose link will be given in the description below of this video tutorial, we explain how to simulate dead reckoning in Python for a simple model of a mobile robot. The dead reckoning implementation approach presented in this video tutorial is far from optimal, and we can say that it is actually a naive approach. However, this naive approach is very useful for understanding the advantages and disadvantages of dead reckoning and learning how to simulate dead reckoning in Python. In the third and fourth parts of this tutorial series, we will present a more optimal approach for solving the dead reckoning problem. But before I start with explanations, I need to mention the following. It took me a significant amount of time, energy, and planning to create this completely free video tutorial, as well as almost 500 free video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thanks a lot. Okay, let's start with explanations. There are a number of definitions and problem formulations of dead reckoning. In this tutorial, under the term dead reckoning, we understand the following. Dead reckoning is a method for calculating or estimating the position and orientation of a mobile robot at a current time step by using information about, number one, the position and orientation of the mobile robot at the previous time step, and number two, measurements of the travel distance and change of orientation of the mobile robot between the previous and the current time steps. Before we mathematically define the process of dead reckoning, we first need to introduce a kinematic model of a mobile robot. This is because the dead reckoning method relies upon simplified kinematics models of mobile robots. This figure shows a simple mobile robot with two wheels. This is the left wheel, this is the right wheel, and this is the robot base. This is actually a graphical representation of a differential drive mobile robot explained in our previous tutorial. A link to that tutorial will be given in the description below this video. The main principle of dead reckoning method that is explained in this tutorial is not only restricted to this robotic configuration, it is also applicable to other mobile robot configurations. In addition to these two wheels, there is a third passive caster wheel that provides the stability of the robotic platform. Passive over here means that this wheel is not actively actuated. However, the wheel can still move around the two perpendicular axes. This third wheel is not shown on the graph in order not to make the graph too complex. In this figure, XY coordinate system is the inertial coordinate system. This coordinate system is fixed. Then, we have this coordinate system XB, YB. This is the so-called body coordinate system. The body coordinate system is also called the body frame. This coordinate system is rigidly fixed to the robot body or robot base. Its center is at the point B. Usually the point B is the center of the mass or the center of the symmetry of the robot body or the robot base. The body coordinate system moves together with the robot. The coordinates X and Y are horizontal and vertical positions of the body coordinate system, or better to say the center of the body coordinate system with respect to the inertial coordinate system X and Y. The angle theta or theta, however you like to pronounce it, is the angle that the body coordinate system XB, YB makes with the x-axis of the inertial coordinate system. That is, the angle theta is the rotation of the body coordinate system with respect to the inertial coordinate system. The angle theta is called the orientation angle or angular orientation. This angle is also called the bearing angle or simply bearing, or heading angle, or simply heading. Since the body coordinate system is firmly attached to the robot body, the angle theta is the rotation of the robot body. v is the instantaneous velocity of the center of the body frame, and omega is the instantaneous angular velocity of the robot. Next, we need to understand what is the robot pose. The robot pose is the vector z defined like this. The first entry is x, the second entry is y, and the third entry is the angle theta. The robot pose completely defines the position or location and orientation of the robot with respect to the fixed inertial frame x and y. From a purely geometrical point of view, the pose defines the location and orientation of the body frame xb, yb with respect to the inertial frame x and y. The pose is also called the kinematic state. The reason for this will be explained later on. The precise knowledge of the robot pose is important for a number of reasons. First of all, it determines the precise location and orientation of the robot in space. Secondly, the robot pose is used for feedback control. Finally, robot pose information is used in other robotic algorithms such as path planning, obstacle avoidance, and SLAM algorithms. In this video tutorial, robot pose is very important for developing the dead reckoning algorithm. Here, we present arguably the simplest possible kinematics model of the mobile robot that can be used to define and solve the dead reckoning problem. We deliberately based this tutorial on the simple kinematics model in order not to blur the main ideas of dead reckoning with too many mathematical details. Although relatively simple, this model can still be used in practical applications. We use two approaches to develop the kinematics model of the robot. The first approach is based on the discretization of the continuous time model of the differential drive robot. This model is derived in our previous tutorial, whose link will be given in the description below. The second approach is based on a simple kinematics derivation and physical intuition. Both modeling approaches result in identical models. However, the second approach is more intuitive since it is based on kinematics and direct physical reasoning. Let us start with the discretization approach. In our previous tutorial, whose link is given in the description below this video, we derived the following continuous time kinematics model describing the robot motion. Here is the first equation describing the change of the x-coordinate of the point B. Here's the second equation describing the time change of the y-coordinate of the point B. And here's the third equation describing the time change of the orientation angle theta. By using the simple forward Euler method, we can approximate the first derivatives of x, y, and theta with respect to time like this. We simply use the forward finite difference to approximate these derivatives. Over here, h is the discretization step, k is the discrete time step, and xk and yk are the horizontal and vertical coordinates of the center of the robot body frame at the discrete time step k. That is, xk is actually x for time equals to k times h. Similarly, yk is y for time equals k times h. Similarly, theta k is the orientation of the robot body frame at the discrete time step k. That is, theta k is theta for time equals to k times h. Next, by using the forward Euler method and by substituting equations for the finite differences into the kinematics model, we obtain these equations. In these equations, Vk is the instantaneous velocity at the discrete time step k, and omega k is the instantaneous angular velocity at the discrete time step k. Here, it is implicitly assumed that the instantaneous velocity Vk and the angular velocity omega k are constant between the discrete time steps k and k plus 1. From the last equation, we obtain the discretized kinematics model of the robot, and here it is. In these equations, we need to observe the following. This product, that is Vk times h, is the distance traveled in the direction of the velocity vector Vk. The velocity vector is actually determined by the intensity given by Vk and direction determined by the angle theta k. It should be kept in mind that the velocity vector is constant. Again, this is very important. The velocity vector is constant between the time step k and the time step k plus 1. The distance traveled between the time step k and k plus 1 is denoted by sk. That is, sk is equal to vk times h. Since omega k is the angular velocity, the product omega k times h is the rotation angle of the robot body between the discrete time step k and k plus 1. We denote this angle by delta theta k is equal to omega k times h. Finally, by using the last two equations, the final discretized model of the robot kinematics takes this form. The model consists of three equations. The first equation describes the change of the x-coordinate of the robot base in time. The second equation describes the change of the y-coordinate of the robot base in time, and the third equation describes the change of the orientation angle of the body coordinate system in time. If we ignore the last equation in our model, the resulting two equations have the following form. These equations describe the translation of the robot body along the direction of the instantaneous velocity vector. That is, they describe what happens from the current time instant to some next time instant, and the robot moves along the straight line. Here, the orientation angle theta k is remaining constant. On the other hand, if we ignore the first two equations, we are left with a single equation given over here. This equation describes the rotation for the angle of delta theta k. That is, the motion is decomposed or decoupled into translation and rotation. And this is a very well-known fact in kinematics and dynamics of motion of rigid bodies in a plane. Namely, the complex motion of a body in a plane from one pose to another can be decomposed into translation and rotation. Let us now use this principle to rederive the kinematics model by using a more intuitive approach that does not explicitly rely upon the model discretization. We formally decompose the motion of the robot from the starting point at the discrete time k to the end point at the discrete time step k plus 1 as follows. From the starting point A to the end point B, the robot moves along a straight line. That is, during the motion from the point A to the point B, the orientation angle theta k is constant and the position coordinates x and y are changing. At the point B, the orientation angle theta k is changed such that the orientation becomes theta k plus 1. This is just a formal mathematical decomposition of the motion. However, in practice, the actual motion between the 2 points might not look like this. That is, this is an approximation of motion that enables us to mathematically analyze the geometry and kinematics of motion. However, if the time interval h between the time instants k and k plus 1 is relatively small, this formal decomposition relatively accurately approximates the true motion. Also, it's very important to keep in mind that at the time instants k and k plus 1, the locations and orientations correspond to the real locations and orientations of the robot. What happens in between the time step k and k plus 1 cannot be exactly modeled unless a more mathematical model is used. To repeat, from the mathematical point of view, the motion is decomposed into a series of straight line motions and orientation changes. Let us illustrate this with this example. Here is our robot, and this circle over here represents the center of the body frame. The goal here is to move the robot from the point A to the point C. The first step, while we are still in the point A, is to adjust the orientation θ1 such that the robot can move along the straight line from the point A to the point B. Here is the situation. We rotate the robot and we keep on rotating until we can move along the straight line from the point A to the point B. Then in step 2, we move from the point A to the point B along the straight line for the distance S1. In step 3, we adjust the orientation of the robot for the angle θ2 such that we can move along the straight line from the point B to the point C. Then, in step number 4, we move along the straight line from the point B to the point C for the distance S2. Next, we develop the kinematics model of the robot that mathematically describes this motion. Consider this figure. From the discrete time step k to the discrete time step k plus 1, the robot travels from the start to the end positions shown over here. During that time interval, the robot has traveled this distance of sk. Under the assumption that the orientation θk remains constant from the time instant k to the time instant k plus 1, from this geometry and by using basic trigonometry, we can establish these two equations. For example, from this figure, we can see that xk plus 1 is actually xk plus sk cosine θk. Similarly, yk plus 1 is yk multiplying sk times sine θk. These two equations describe the location of the robot at the time step k plus 1, under the assumption that the robot was at a location xk, yk at the discrete time step k, and that it has traveled the distance of sk between the discrete time steps k and the discrete time step k plus 1. In addition to these two equations, we need to add an extra equation describing the change of the orientation angle θ. Namely, over here we need to perform rotation for the angle delta θk. That is, the final orientation at the discrete time step k plus 1 is actually θk plus delta θk, and that's precisely this equation. Now, by combining the previous two equations, we obtain the final kinematics model of the mobile robot, and here it is. And that's precisely the kinematics model obtained by using discretization of the equations. Now we are ready to formulate the dead reckoning problem and to state its solution. First, we need to define the pose vector. The pose vector, denoted by zk, is defined like this. It is a vector composed of xk, yk, and θk. Next, let us define an estimate of the pose vector. The estimate of the pose vector, denoted by zk hat, is defined like this. It consists of xk hat, yk hat, and θk hat. xk hat, yk hat, and θk hat are estimates of xk, yk, and θk that are computed by using the dead reckoning method. The dead reckoning problem can now be formally defined. Here is the dead reckoning problem. Let us assume that the estimate of the robot pose vector zk hat at the discrete time instant k is known. Number 2. The measurements of the travel distance sk and the orientation change delta θk are obtained at the discrete time step k plus 1. The initial values of x0, y0, and θ0 are known accurately. That is, the initial pose vector z0 is known accurately. Then, under these assumptions, obtain an estimate of the robot pose vector zk plus 1 hat at the time instant k plus 1. Perform the estimation tasks recursively for k is equal to 0, 1, 2, 3, etc. To solve this problem and to implement its solution in Python, we need to clarify several important aspects of this problem. First of all, we need to explain what is odometry. Often in robotics literature or during the conversation between robotics engineers, you will hear the term odometry. People use this term in different contexts and have different understandings of this term. Under the term odometry, we understand the process of using the data from sensors to estimate or measure the travel distance and heading direction or orientation of the robot. Some people restrict the term odometry only to the sensing or measurement process, and some people under the term odometry understand the complete process of sensing and estimating the distance and heading direction. In this tutorial, under the term odometry, we understand both the sensing and estimation processes. In that sense, dead reckoning is a type of odometry. Now, the main question is how to measure the distance traveled sk and the change of angle delta theta k. We can measure sk indirectly by using wheel encoders. By knowing the encoder resolution, wheel geometry, and number of detected encoder pulses, we can obtain the measurement of sk. Also, we can measure sk by using some other method. More about this in our future tutorials. On the other hand, we can measure delta theta k by using a gyroscope, compass, or even using two wheel encoders and combining their measurements. Again, more about this in our future tutorials. One of the most important issues that limit the accuracy of odometry and dead reckoning is that measurements of sk and delta theta k contain errors. For example, the wheels of the robot can slip. However, the encoder will detect the wheel rotation angle, and the travel distance computed on the basis of the detected wheel angle will not correspond to the actual travel distance. Also, some random effects can occur that can limit the accuracy of sensors. This means that in our model, we are not directly measuring sk and delta theta k. Instead, we are measuring their corrupted versions sk tilde and delta theta k tilde that are defined like this. Sk tilde, that is the measured value of the travel distance, is actually the true value of the travel distance plus ek, and ek is a noise term. Similarly, the actual measured change of delta theta k, denoted by delta theta k tilde, is the true value of delta theta k plus this noise term over here. We assume that both ek and qk, that is, these two noise terms, are normally distributed with zero mean and known variances. That is, we assume this, where sigma e squared and sigma q squared are the variances of ek and qk respectively. Again, here it's very important to keep in mind that true values of sk and delta theta k are not known. The only quantities that we know and that we can use for solving the dead reckoning problem are their measurements sk tilde and delta theta k tilde. These measurements are corrupted by the measurement noise represented by ek and qk. In the sequel, we present the simplest possible approach for solving the dead reckoning problem. This approach is suboptimal and in some sense naive. However, this approach is still very useful since it can give us the first idea of the behavior of the dead reckoning. The idea for solving this problem is to use the kinematic model, that is, to use this model and to substitute the true values of sk and the angle change delta theta k by using their measurements sk tilde and delta theta k tilde. Also, the exact values are substituted by their estimates in order to obtain a recursive relation for computing the estimates. That is, instead of xk, yk, and theta k, we will have hats here since we are computing estimates. The naive dead reckoning estimator has this form. Here it is. Again, instead of sk, we use the measurements, sk tilde, and instead of delta theta k, we use delta theta k tilde, that is, we use the measurements. And again, we replace xk, yk, and theta k, that are true values, by their estimates that we are actually computing. We initialize these three equations with the exact initial value of the location and the orientation. That is, we assume that initially we know the exact value of x0, y0, and theta 0, and we initialize the estimates by using these exact values. And after that, by using the incoming measurements, sk tilde and delta theta k tilde, we simply propagate these equations and we use the past estimates to compute the future estimates. That is, to compute the estimates at the time instant k plus 1. And that's it. That's the simple idea of that reckoning. Again, this is a naive approach since we are not filtering anything over here. We are just propagating through the model. Okay, that would be all for today. I hope that you like this video. If you like the videos I'm creating, please press the like and subscribe buttons.